Welcome to this lecture. This is the fourth lecture of week 7. In this week, we have been focusing on further properties of weak convergence, and we have also seen the extension of these ideas to higher dimensions. In this lecture, we are going to focus on a very specific example of weak convergence, and this will connect to our earlier discussion on law of large numbers. So, without further delay, let us continue the discussion using the lecture notes. So, in this lecture, we are going to talk about something called the central limit theorem. So, what is the idea? So, the idea is that we are going to start with the law of large numbers, which states certain kind of a convergence for some certain sequences of random variables. To be exact, we are going to start with this very simple situation of the weak and strong law of large numbers that we have already discussed in week 5 earlier. So, this is this setting that we are working with some IID sequence of random variables, which are defined on some given probability space, and if we assume that this sequence of random variables have finite mean, then what we have mentioned earlier is that Sn over n, Sn being the partial sum, that quantity Sn over n is giving us now the sample mean, and that goes to expected value of x1 as n goes to infinity, and this mode of convergence can be taken as in probability convergence or almost sure convergence. When we are discussing the results in terms of in probability convergence, that is the weak law of large numbers. When we are discussing the convergence in the sense of almost sure convergence, that is the strong law of large numbers. Now, given this convergence result, what we are now interested is in the rate of convergence of this convergence. So, let us clarify what we mean by rate of convergence. So, we go back to our discussions in the convergence for sequences involving real numbers, and we will take motivation from that and then try to get a similar result when we are considering sequences of random variables. So, let us start with some sequence a n of real numbers, given that it is converging to some real number a. Now, what we are interested in is the fact is that this quantity goes to 0, that is for certain, because as long as we are saying that a n is converging to a. So, that means that these numbers modulus of a n minus a are going to 0 as n goes to infinity. But we are now asking how fast does this quantity go to 0. Stated in another way is that suppose I want my number to be smaller than some epsilon, how many n do I need to look at before we start observing that this a n minus a modulus value of that is smaller than that epsilon. So, that is part of the definition of the limit, that given any epsilon positive, we can find some number capital N such that after that stage onwards we are going to have that this number is small, but we are now interested in the explicit value of the number capital N, and this is essentially trying to characterize how big this number modulus of a n minus a is for large values of small n. Now, if we take some standard sequence b n, we may focus on certain kind of inequalities of this type. So, let us look at this inequality, that we are looking at modulus of a n minus a divided by modulus of b n, that quantity. Now, we want that for large values of n, we want this to be bounded between two constants which now call as C1 and C2. So, if these two constants are two non-negative constants, then what will it give us is that it will tell you that modulus of a n minus a is landing between C1 times mod b n and C2 times mod b n. So, in practice, if you take a standard sequence b n to be 1 by n to the alpha for some alpha positive, if you take such a thing, then what we are essentially trying to ask is whether for large enough n can we find two constants C1 and C2 such that these terms are landing between C1 by n to the alpha and C2 by n to the alpha. And if we can manage that for some constant C 1 and C 2. This will give us some idea of modulus of a n minus a for large values of n. So, that is how we would like to understand how fast does a n minus a, the modulus value of that, go to 0. So, this is in the form of these standard terms n to the alpha. Now, often instead of this directly getting this inequality, what we are trying to show is that we would like to establish the existence of a limit of this form. Now, if we can establish a limit of this form and let us say this number is some small b, then what does it mean? It means that given any epsilon positive for large enough n, so n greater or equals to some capital N, what we are going to have is that n to the alpha times a n minus a, that quantity falls between the numbers b plus epsilon and b minus epsilon, right. So, that is the idea of the convergence. Now, here as long as we are talking about these non-negative numbers, if it so happens that b is strictly positive, then we will choose some epsilon such that b minus epsilon is also positive, and therefore, b minus epsilon will play the role of C 1 and b plus epsilon will play the role of C 2 as stated above. So, instead of directly looking at the inequality, we can also try to establish a limit of this form, and if we get that the limit b here is positive, then we will be able to get the estimates of the type we want. So, therefore, all of our subsequent discussions will now focus on obtaining limits of these types. Now, motivated by this idea that for the sequence of real numbers, we can try to get a rate of convergence type result just by looking at limit of n to the alpha multiplied by the modulus value of the error terms. If we can establish such a limit for a sequence of real numbers, that gives us some idea of about the rate of convergence. We now try to do the same when we are dealing with a sequence of random variables. Let us see. So, what we now do is that we are now going to replace this sequence of real numbers a n by the sequence of random variables and the corresponding limit. So, a n will be replaced by x n and the limit a will be replaced by a random variable x. Now, in the sense of random variables, we have multiple modes of convergence that we have already seen. Now, here what we are going to focus on is some mode of convergence, and then in that mode of convergence we are going to ask about the rate of convergence type result. And in this case, what we are going to do is to obtain a random variable y such that we actually obtains as a limit of this type. So, here b n as before will stand for some standard sequence of real numbers. So, we are not taking them to be random variables, but taking this standard sequence of real numbers, we are going to look at the errors from the original sequence of random variables, and we rescale it by this standard sequence of real numbers b n, and what we would want is that this limit holds and this goes to some random variable y. And again this mode of convergence may be some mode of convergence for the sequence of random variables. Now, here if we can obtain such a thing, then in principle we can also look at the corresponding modulus values and take the limits. So, this is in principle an application of the continuous mapping theorem, which is true for almost sure convergence, convergence in probability and weak convergence. Also, we can revisit some results in terms of the modulus of the random variables when we are considering the LP convergences. So, for LP convergences, recall that we cannot talk about the continuous mapping theorem, but still we may be able to say something about this kind of modulus of the quantities when we are talking about the LP convergences. That we can see depending on problem to problem. But in principle, what we are going to say is that our idea would always be to look at limits of the former type, where we are looking at the scaling of x n minus x divided by b n, and as n goes to infinity we want to see it as a some random variable. Here it is important to note that all the random variables we are taking to be defined on the same probability space. So, that x n minus x is defined. Now, let us move ahead and go back to the original setting that we are going to talk about. So, what we are interested in is to figure out the rate of convergence for the law of large numbers, and results that we obtain which will try to answer this question. These type of results are typically called the central limit theorem, and in short we are going to call them as CLT. Now, let us make a note of this fact that if we are working on a probability space omega f p, and if we are given a sequence x n of IID random variables, all of which has finite second moment. So, that all of them are in L2, and we can talk about the corresponding variances. Assume that the variance of these random variables are strictly positive. In particular, this will mean that our random variables are non-degenerate. Now, look at the corresponding sample mean, which is again S n over n, which is just this quantity. Now, here we note the mean and variance about the sample means. So, expected value of x n bar is nothing but expected value of x 1, and variance of x n bar can be simplified using the independence of the random variables, and at the end we end up with this quantity as the explicit computation of the variance of the sample mean. And here it is noteworthy that since variance of x 1 is some constant, then as n goes to infinity this quantity goes to 0 as n goes to infinity. So, now if we look at these centered and scaled random variables like this, that we are looking at this quantity modulus of x n bar minus expected x 1. So, that is first centering, and then we rescale it by the square root of the corresponding variance, which we rewrite in this form. So, first we write square root n, that comes from the computation of the variance of x n bar, and in the denominator we are just left with this term. So, this is a centered and scaled random variables, meaning this is also a normalized random variable with mean 0 and variance 1. We can also rewrite this expression in terms of original essence like this. So, we will come back to these expressions immediately in the next result that we are going to discuss. But the point that we want to highlight is that for each positive integer n, these centered and scaled random variables are normalized, meaning they have mean 0 and variance 1, and this fact is independent of the distribution that we are taking. So, here we have taken a IID sequence of random variables x n, and other than the existence of the second moment being non-negative and also the variance of x 1 being positive, we did not ask for any other conditions on the common distribution of these random variables. And here what we are saying is that these kind of centering and scaling are giving us some normalized random variables. And the next statement, which is a very important result, is going to tell us something about the limiting behavior of these normalized random variables, and this is called the Lindeberg-Levy central limit theorem. So, the idea is this: we are going ahead with the same setting, that we have a sequence of IID random variables in L2, and we are going to call the variance of x 1 to be sigma squared. Our standing assumption will be that this quantity is positive. Now, let us look at this centered and scaled random variables. Again, this can be visualized as the centering and scaling of the original sequence of partial sums S n. So, just rewriting this expression we get this. Now, again rewriting this, we have already seen that we get this. So, all these expressions are the same. Now, what the statement says that as n goes to infinity, this quantity converges weakly to a standard normal random variable. So, that is a very important statement that says that in the setting of weak convergence, these quantities go to a standard normal random variable. So, here even though the law of large number setting was that the original convergence we were considering in terms of convergence in probability, or the almost sure convergence, we cannot really talk about that setting to talk about the rate of convergence, but we are trying to talk about a rate of convergence at least in the form of weak convergence. That is the interpretation of this result, and we are going to see some very interesting restatements of this formulation. Let us see. So, what we are now saying is that since the limit random variable is normal with mean 0 and variance 1, we are going to restate certain things in terms of the corresponding distribution functions. So, first of all, the distribution function of the Gaussian random variable that we are considering as the limit, this is continuous everywhere, and therefore, what we will conclude is first of all, through the weak convergence, the corresponding limit of the distribution functions hold for all points in the real line, because it does not have any point of discontinuity. So, therefore, the points of continuity is the whole real line, and therefore, we must have the corresponding convergence of the distribution functions holding for all points in the real line. So, here capital F subscript capital Z denotes the distribution function of Z, which is following normal 0 1. Now, going back to the idea of the result, if we rescale things by a constant sigma, that is playing the role of the standard deviation, what we will now observe is that if we multiply the relations by sigma everywhere, then the corresponding limit will be sigma times Z, which is following normal with mean 0 and variance sigma squared as n goes to infinity. So, sometimes the results will be stated in this form also without scaling by the number sigma. All right. So, let us now restate the central limit theorem in another format. So, if we look at two real numbers a less than b, then we look at the underlying measure that is associated to this kind of left open right closed intervals. And here again note that the limit distribution or limit random variable that we are looking at, that is continuous. Therefore, this kind of quantities go to the corresponding probabilities given by Z, but this can be rewritten in the form of the difference of the standard normals distribution function, which can also be expressed in terms of the standard normal PDF, which is this familiar quantity, and that we are integrating on the interval a to b. So, that is the expression here. So, we have seen some very interesting restatements of the central limit theorem, and these restatements are often useful in practical applications, which we are going to discuss in the tutorial of this week. Now, we note another important point about the statements is that we have considered the situation that variance of these random variables are positive, but in the case when this variance is actually 0, what happens? Actually happens is that all these random variables turn out to be degenerate at some constant. So, since all these random variables are independent and identically distributed, all of these are now identically supported on this singleton point small c. So, the corresponding law is the Dirac measure supported at C. In particular, what we are saying is that with full probability all these random variables are independent, that is fine, but with full probability the random variables are taking the value small c, and therefore, the sample mean is also small c with full probability. So, therefore, there is nothing to discuss here about the limiting behaviors, because all that turns out is that all these quantities are constants. There is no variations are included in these statements when variance of these random variables are 0. So, we will consider the general case when variance is actually positive. All right. Now, we want to keep this point in mind that we have motivated the central limit theorem as a rate of convergence result for the law of large numbers. Now, the idea is that law of large numbers is giving us some kind of convergence, and we are asking about the rate of convergence. So, in principle, if we can say something about the rate of convergence, this should ideally be a stronger result than the original statement, which is the law of large numbers. In fact, in a later lecture we will come back to this point and discuss the proof of law of large numbers through the central limit theorem. For that we require some additional results which we are going to discuss in a later lecture. So, we will come back to this point that central limit theorem in principle is a stronger result than the law of large numbers. Alright. So, let us see the proof of this Lindeberg-Levy CLT, which is also sometimes called the classical central limit theorem. Alright. So, now here what we want to do is to establish a certain type of weak convergence. Now, to establish the weak convergence, what we are going to do is to prove one equivalent condition which we have discussed earlier. We are going to show the pointwise convergence of the corresponding characteristic functions. So, that is our method of proof, and then once we get this, the proof will follow from the Levy's continuity theorem, which we have discussed earlier in theorem 6 of week 6. Alright. So, let us now manipulate the characteristic function of the sequence that we are interested in. To start off with, let us look at these expressions which are appearing in our statements. Now, here you note that we can rewrite it using this form where all the random variables has been centered by the corresponding mean. Now, here without loss of generality, therefore, we can just focus on the inner quantities which has mean 0. So, therefore, what we are going to do is to simplify our argument by taking that the mean is actually 0. So, there is no loss of generality if we assume this, but this will help us in the notational setting that we will get some smaller amount of expressions to simplify. So, now if we take the mean to be 0, what we are now interested in is this quantity that as n goes to infinity, what happens to this sequence of random variables. Now, let us look at the corresponding characteristic function of this random variable. So, we compute this at all points u in the real line. So, this is the definition that we are writing for the corresponding characteristic function. So, this is the expectation of exponential of I times u times the actual random variable. Alright. But now, Sn, remember, this is the sum of independent random variables x1 up to xn, and therefore, once you put that summation in the exponent here, then it splits because all these random variables are independent, and therefore, what we will end up with are the product of the corresponding characteristic functions. But now, note that all these random variables are actually identically distributed. So, therefore, the corresponding characteristic functions that we are computing here are actually same, because the distribution of x1 and x2 are the same, the corresponding characteristic functions are also same. So, therefore, for each term we are going to get a term of this kind, but since we are getting this for n different random variables, we are just ending up with to the power n. So, that is the product we have simplified here. Now, here it is important that we are using the both the things, that we are using the independence of the sequence xn as well as the identical distribution feature of this sequence. Now, we go back to certain properties of the characteristic function. So, we have discussed this earlier in theorem 7 of week 5, that given certain information about the moments of the random variable, we can expand the characteristic function in a neighborhood about 0. So, here the result will be stated in this form, that since we are rewriting everything in this characteristic function. So, that is the term that is actually appearing from the simplification that we have looked at. So, let us expand this using the moment information that we are already given. So, now we have to simplify this term here. So, if you expand this out up to the second order, so this is essentially a Taylor expansion type result. So, if we expand this, we look at the first two moments of the random variable, then the remainder term will be a small o of this. So, here the result is true as long as u goes to 0. Now, here you note that expected value of x1 that we have, that is we have assumed to be 0 now, and moreover expected value of x1 squared, that is nothing but the variance of x1 now, because the mean we have assumed to be 0. So, therefore, this quantity is nothing but sigma squared. So, if we simplify this expression for the characteristic function, we will end up with this calculation now, that if we now work with fixed value of u letting n go to infinity, what we are going to have is that mod u by sigma root n, that quantity also goes to 0. So, this is now happening for fixed value of u. So, let me clarify the distinction of the result that we are seeing for n going to infinity and u going to 0 situation. So, in the previous setting, when we are talking about the expansion of the characteristic function, we are keeping the n fixed and letting u go to 0. But now, if you let u fixed and let n go to infinity, the same term again goes to 0, which is what we really require in the Taylor's expansion that we are looking at here. So, therefore, if we now keep the u fixed for arbitrary such u letting n go to infinity, we now have this rate for the characteristic function of interest. So, first of all, this is written as a product of all these characteristic functions, but the inner characteristic function here has now this expression. So, here we have used the actual values of the moments of x 1 of order 1 as well as order 2, and that is the simplified expression that we end up with. So, here as n goes to infinity, this will now go to exponential of minus u squared over 2. So, this is a very standard limit coming from real analysis. So, please check this. But now, we revisit this function as the characteristic function of the standard normal random variable z, and since this equality is true for all u in the real line, therefore, what we are saying is that as n goes to infinity, these quantities are converging pointwise. So, this is the correction that will be made in the lecture notes here, that as n goes to infinity, these quantities are actually converging pointwise to the characteristic function of the standard normal random variable, and that is what we wanted to show, that we have the pointwise convergence of the characteristic function. So, therefore, Levy's continuity theorem gives us our result that we wanted. Finally, we look at a comment about the central limit theorem that we have just discussed. So, in this central limit theorem, other than the finiteness of the second moment, we did not really require any other assumption on the common distribution of these random variables. So, we are working with some sequence of random variables which are IID and having the variance to be positive. So, that is the minimum requirement that we ask, and we did not put any other condition on the distribution of these random variables. However, the statement says that the limit random variable must be Gaussian. So, in practice, what we are going to do is that in order to estimate certain calculations or obtaining certain data from certain populations, when we do not want to make any assumptions, we can approximate this for large enough value of n, that the Gaussian random variable can play the role of such data for involving sample means, and this only requires certain second moment assumptions. So, that is all we will require, and this in practice is very useful. So, we finish with one explicit calculation as an application of the central limit theorem. So, let us say my IID random variables are coming from Poisson 1 distribution, then immediately happens is that the mean and variance is 1. So, this is a very standard fact about Poisson random variables. Now, consequently, let us now look at the sequence of partial sums. So, here S n, which is summation of x 1 up to x n, that will follow the Poisson distribution with parameter n. So, therefore, expected value of S n will be n, and also the variance will also be n. Now, if you appeal to the central limit theorem above, we just have to look at these centered and scaled quantities, and here what we are saying is that these quantities must go to a standard normal random variable in the sense of weak convergence as n goes to infinity. And in terms of x n bar, the sample mean, we can also rewrite this result like this, that square root n times x n bar minus 1 converges to a standard normal random variable, as n goes to infinity, but the sense of convergence is the weak convergence. So, in this lecture we have seen a very interesting example of weak convergence, which is giving us certain kind of a rate of convergence for law of large numbers. So, in the next lecture we are going to discuss certain problems involving these results that we have already seen in this week, and in the next week's discussions we are going to discuss some further generalizations of this central limit theorem. We stop here. Thank you.